So I'll put since right now every week I'll put my video on the YouTube. So we start our lecture. So today is November 7th, so week 9. So week 9, actually we'll teach you about the LDA. But today I just try to finish the PCA. So I'll spend 1 hour to finish the lecture PCA. Next week we'll talk about LDA and vector quantization. And final one, I will teach you Hindermarkov model. Hindermarkov model. I did not teach Hindermarkov model for 3 years. But right now I come back to teach HMM because the deep learning right now they have a new technology called Mamba. A new deep learning technology, and Mamba is from Hindermarkov. So I will teach you guys again. Mamba is important for small, very small object detection. It's a new method. Mamba is M-A, forget how to spell it. Mamba, M-A, not M-A-B-A. I missed one carrying in the channel, I forget. Okay, let's continue to talk about the PCA. So last week, we talked about the PCA basic concept. Today I will teach you the mathematics equation about PCA. So PCA is very powerful because inside PCA eigenspace. So eigenspace is very useful, very powerful. And it's kind of a factorization, instant factorization by using singular value decomposition. So right now in the world, the best face recognition method is deep learning, but eigenspace. Deep learning eigenspace. So right now the best recognition method is using the deep learning, but inside the deep learning is the eigenspace. I'll explain to you. So suppose I have a MIT person, MIT students. This from one paper. This paper is here. Each lecture I have a papers. So this paper is here. So the MIT guys. So I teach you PCA, but right now in deep learning, we use this GAN, G-A-N. So GAN is from PCA, but better than PCA. I will explain to you why. But why I want to teach you PCA? Because if I only teach you the deep learning, you don't know the fundamental thing about the GAN. You just know the loss function. So that's a problem. So right now, you guys, if you learn the deep learning, you only know the network. You only know the loss function, because loss function, you solve the loss function, you get a result, but you don't know the reason. You don't know the principle the loss function. So I teach you why the gain inside the gain, the fundamental thing is the PCA. So I think that's the reason I teach you. Okay. So suppose we have a 16% here, and this is for not for detection. Detection is a two class. Class is a phase, non-phase. That's detection. Okay. Recognition is a one to many. So if I have a 16%, and how can I recognize each one? But this one is simple, okay, because it's about year 1991, suppose that one. It's very old. So right now we not only have a frontal view of face, right? We have a side view. We have different poses. So right now, our face recognition can recognize a person under different poses. What do I mean poses? When you study the paper, they tell you they can recognize under different poses. Pose is meaning you have a rotation. You have a rotation. That's mean pose. So that's kind of a extrinsic parameters. Back to here. So right now, suppose in the database, in the training data, I have a 16%. Okay. So, but in our class, we have 250 students. So if I want to do the face recognition, I need to collect 250 faces. But actually, that's not enough because sometimes under different lighting. So probably each person, I need to take 5 photos under different lighting, under different poses for face recognition. But here, the simple way is suppose 16%. I want to recognize use this training data. After I training eigenspace, and then for the inference, is for the detection. For the test, I take one photo. I want to recognize whether this photo is one of the students. Sometimes, if you are not inside here, you will be rejected. Okay, so that's for the example is face recognition. However, for example, if each pixel is a 128 pixel, right? There's a dimension. And when I take a photo, I want to recognize who is who. And then I need to compare 16 times, right? 16 times each one. And to compare and find, and I to do a similarity measure and find the minimum value. And for the minimum values is less than, the minimum value, is less than some threshold. I say, oh, that's a person. So the comparison for the similarity measure is a pixel by pixel, is 128 by 128. But I need to compare 16 times. Can I reduce, if I have one person, like a city, like a surveillance, okay, a city, I want to recognize a criminal, 就是我要找那个罪犯，那犯罪的人，100万个人，这 city。Can I compare it? Because each time I catch one image, I need to calculate 1 million times. I need to do the match one by one. And then for each image, suppose 128 pixels. So let's spend a lot of time. So what we can do is if we use singular value decomposition, I project those bases, project to the eigenspace. That's meaning if I create based on the 16% I will spend here. So the reason is one. So suppose I have a M, capital M is a 16. That's meaning we have image 1, V1, V2, V3. So total have a 16 here. M is 16%. Equal to this one. What is this one? It's a new space we call eigenspace. So we have a 16 bases. I can create eigenspace. In the eigenspace, I also have a 16 eigenfaces. So I have a n is 16, so I have an eigenfaces is 16. Each eigenface is 2D, but in eigenspace, it's one direction, one axis, so it's 1D vector. 2D image is like a transformer, like a token. Original page, 2D page, we can shape to token. Token is 1D. So in this case, if the image size is 128 by 128 is 2D, actually, I can be like a 1 by 1 by 128 by 128 dimension, so it's a 1D vector. 就自己注意一下，2D 的东西都可以变成1D 的向量。这一个轴， so this one axis is eigenface 1, the second axis is eigenface 2. Okay, so that's meaning I can project to the I can create the eigenspace. They are 16 dimension. Each dimension is one eigenface. Eigenface look like this one. This eigenface. Okay, so I have 16 eigenfaces. And then the first eigenface represents what? Because each eigenface will corresponding to one eigenvalue. Eigenvalue meaning the variance between those 16%. What's variance? Variance meaning the difference. Variance equal to difference. That's meaning the first eigenface corresponding to eigenvalue 1. And suppose eigenvalue 1 bigger than we do the sorting. Eigenvalue 1 is the biggest eigenvalue, bigger than eigenvalue 2, 3, 4. We are in order. So that's meaning the first eigenvalue, they are difference among 16%. 就是说第一个 eigenface, the first eigenface, they corresponding to the largest eigenvalue, meaning those among from those 16%, what's the biggest, what's the maximum difference between 16%? 所以意思是说，第一个 eigenvalue correspond to 第一个 eigenvector 的 eigenface， 这个 eigenface 里面的这16个人的最不一样的东西。I say again, after you transfer to the eigenspace, you do the sorting based on the eigenvalue. So suppose the eigenvalue 1 is the biggest eigenvalue, bigger than eigenvalue 2, 3, 4, until eigenvalue 16. And that's meaning the first eigenvalue corresponding to the first eigenvector. This eigenvector meaning the most difference among the 16%. So for example, our eyes, when we do the classification of the cognition, what's the most difference? Which feature, feature are the most difference? Why? Because we will find in the first eigenvalue, in the eyes region, they have a higher value, higher feature map value. That's all in the eyes region. The feature map equal to eigenface. Okay, in the eyes region, the value is higher. So it's meaning very different. The second eigenvalue corresponding to second eigenface, you'll find the mouse. have a higher attention, higher difference value. The third one probably is eyes plus nose together. So that's the main principle. Is meaning SPD is meaning they try to extract, not only extraction, they also try to do the independent, because each eigenvector are orthonormal. Orthogonal means independent. So they will do the extraction. Okay, so the first eigenvector, they pay attention on the eyes, the face of the face. The second eigenface, attention on mouth. The third one is the eyes plus mouth. The fourth one probably mouth plus nose. Okay, and they do the next kind of extraction, attention things. And you will find out in this example. So we have original have a 16 faces. We create 16 eigenfaces. However, we will find the eigenvalue after 8 eigenvalue. Their eigenvalue is close to the 0, very small. That's meaning you can ignore. Okay, so that's meaning we are from here, original 16%, we can reduce to only 7 eigenfaces. Rest of eigenfaces, because their eigenvalue are too small, you can delete it. That one. Okay, so that our dimensions from 16 become only 7 eigenfaces. If your data is bigger, suppose we have 1 million %, you will find out the dimensionality reduction will become bigger. So my experience, I have one experience here. When I do the facial expression recognition, suppose I have almost 1,000 faces, and I can reduce only the first 10 eigenfaces. So my dimension reduced from almost 932 to 10。就是说，你的eigen有个特色，当你的 data 越大量的话，它可以减少的空间越大，因为萃取出来的资讯 variance 会越明显，这是它的好处。我想是大量资料，所以是这里。So original we can reduce to m prime. M prime in our case is 7. So we finish our eigenspace creation. So our eigenspace is from 16 eigenfaces, we reduce to only 7 eigenfaces, only 7 dimensions. And second one is actually the process here. I write the process here. Okay, so the first one, we want to create covariance matrix. So you collect all 16% together, image together, become one covariance matrix. 就是你把16张影像 remember 2D image will become 1D vector and collect all together and create a covariance matrix. And based on covariance matrix, we can create eigenfaces using singular value decomposition. Is it here? This is a covariance matrix. This original matrix reduce subtraction with the mean value, mean of the faces. This means 16 faces into the average mean, and then you do subtraction, and then we do SVD become U WVT. Okay. U is the eigenvector. W is eigenvalue. V here, V equal to U because it's symmetric matrix. If it is a symmetric matrix, U equal to V. Okay, so after you create eigenspace, then we reduce from, so in this case, from M to N prime. So this is your final eigenspace. After you have an eigenspace, and then we will do create the projection weight vector. Projection weight vector. What's the projection weight vector? Is this one here. So for each original, I want to tell you the construction. Why GAN can do reconstruction, the same PCA can do reconstruction. After, so here, so each phase equal to linear combination of all eigenphases. And their corresponding coefficients is the weight, we call projection weight. 也就是说你原来的任何影像可以投影到 project to the eigenspace. So give you any image 128 by 128. So any image you can project meaning inner product. So you do the inner product. Any image here, you project to eigenspace. It's meaning this basis function eigenphase 1 until eigenphase 7. And their corresponding weight we call projection weight. This is easy because this dimension is 128. Eigenphase dimension 128 into inner product. Right? Remember, 1 because 2D become 1D. So 128 by 128 become 1D. So you have vectors 1 times 128 or 128 become 1 vector. So image, so this image, you inner product is eigenphase 1. You have only 1 by 1 by this value for projection weight in first eigenphase. Overall, you have 7 eigenphases, so you can create 7 dimension projection weight. 你有7个人脸，eigen的人脸嘛？那你原来人脸 project 到第一个人脸就只有一个词，那有7个人脸就得到一个7个 eigen value 的词。So your projection vector is only 7 dimension. So this 7 dimension represent your original image. So that's meaning your dimension reduction is the original image is 128 by 128. Right now become only 7 dimension. So your dimension reduced a lot. Okay. So that's meaning each input image you project to the eigenspace, you can use this both projection weight to represent original image. Only 7 dimensions. So it reduce a lot of space. So that's here. Only 7 dimensions. And here I try to explain to you is that here is that suppose this eigenvector, right? Eigenvector 1, this 1 image, eigenvector 2 image, and then you cut after 7 eigenfaces, cut it, and you just chip the first 7 eigenfaces. Just I try to explain to you this one. So after you have a projection weight, and then we do the classification based on this one, the likelihood probability. So original, suppose this is the Gaussian model, and you want to do the likelihood probability comparison. So this original image, suppose input input F. Input is F. This is the likelihood. Likelihood is the input I. And your face template here. This is the template. So original, each I or F, the dimension 128 by 128. Right now, no. Right now, only 7 dimensions. So you compare 7 dimensions here, 7 dimensions. So your calculation will be very fast. Okay, that's the purpose for the PCA. So PCA or eigenspace has a 2 purpose. The first purpose is from original space. You try to extract the important component we call principal component in the eigenspace. This first step. The second step is each image you project to the eigenspace, you reduce, we call dimensionality reduction. You reduce a lot of dimension for comparison, for similarity manager purpose. So 2 purpose. Sorry, there are 2 purpose for PCA. That's it. So that's a PCA purpose. That's a SPB purpose. That's a GAN. So GAN basically their fundamental principle is here. So this process here, procedure for the eigenspace here, I just explained to you. You have, first of all, you put all the data, training data together, become a big covariance matrix. And then based on this covariance matrix, based on training data, we create eigenspace. From eigenspace, we reduce the eigenspace, reduce. And then for each image, you project to the eigenspace, projection weight. So the projection weight represent your coefficients, represent the descriptor. Projection weight actually is descriptor. We call SIFT is the descriptor. Here, the same, your projection weight also called your descriptor. And then based on descriptor, you also can do the reconstruction. You also can do the similarity measure. And the last question is, here's the mathematics. How can we use neural network to do that? So right now, you learn the GAN. Actually, in year 19, they already did that way. I'll explain to you. So for the mathematics this way, the first step, we will create the covariance matrix. So for covariance, actually we need to find the average value. So this we have a average mean. So look like this one. Based on the 16%, we try to find the mean value. So PCA is a Gaussian model. PCA is Gaussian model because when we calculate the PCA eigenspace, we need to find based on the covariance matrix. So we need to find the average value and do the subtraction to become covariance matrix by this one. And then we want to do singular value decomposition. So that's a page. So page 30. Page 30. So page 30 is factorization. Factorization is equal to singular value decomposition. So you have a matrix C become U, W, because if C is there, because the covariance is symmetric. So U, W, VT, VT equal to U. If it is not symmetrical, U, W, VT. Okay, but in page 28 and page 29, you just ignore it. because my lecture is about 20 years old. But at that time, I was trying to teach students that this equation, but right now your computer is powerful, so you just put a bigger matrix, it's fine. But 20 years ago, if you put a bigger covariance matrix, the computer cannot calculate the big covariance matrix. 20年前那个电脑跑不动，所以我讲到这个。Right now you don't need to worry about this equation, so you don't need to. You can check this one, but right now your computer is powerful. You don't need to worry about this one. This is just an equation. Covariance matrix. This is a matrix. Okay. This H5. Sorry. H5 is a set of image. Right now you don't need to worry. So phi will the covariance matrix will be A times A transpose become covariance matrix. A is that here. A is a set of faces. A is a set of faces. So A times A transpose become covariance matrix. And you don't need to worry about this one. The economic, it's the same as economic. So we go to page 30. Based on covariance matrix, we can do singular variable decomposition. You call the function, they get you return to eigenvector, eigenvalue. So you are done for the first step. And here just try to tell you is that for each eigen or eigenface is orthonormal. So each axis 每个轴 each axis is orthonormal. Each vector is orthonormal. Orthonormal meaning orthogonal and normalization. Orthonormal meaning orthogonal. Orthogonal meaning each axis is 90 degrees to each other. So that's meaning each axis, if you project, you will become 0. 这每个轴是90度嘛，所以 project 下去的话，那 90 degree this way, because this is space. So this is 90 degree. This is 90 degree. This is also 90 degree. So you have different location angles, also 90 degree. This is one plane, so 90 degree. But if you rotate, because each axis rotates 90 degree. So let's tell you that it's 90 degree. So it's an inner product between two axes. It's zero. They are independent. But what's normalization? Normalization meaning it's a univector. Standard sample. So normal univector. So orthonormal meaning orthogonal and the univector. That's the definition for axis. Axis equal to principal. And you don't need to worry about that one. Those are a long time ago. I just help you to remember how can you calculate eigenvalue, eigenvector. But right now you don't need to worry about that one. And eigen will become this one. After you create eigenspace, so what's eigenspace? Eigenspace, if we go back to last week, if your samples are here, your original 0, here, this is your samples. So each point, each sample point is one face. This face in the space is 128 by 128 space. 就在这是一个高纬度里面的一个点。After you do the PCS, meaning you have a new center here because you minus the average value. So new average value here. And this is first eigenvector. First eigenvector meaning each sample point you project to the first eigenvector. The variance bigger, variance. So each one is separate as away as possible. The first first eigenvector is, meaning each point you project on this principle, this axis, there will be away as possible. The second axis is the same. The third one is the same, but they have become closer, closer, closer. So that's the meaning for the PCA. So PCA is one. They will try to find the axis. The axis will you have a biggest variance. This one. So that we to this called SVD is called actually the factorization, 因式分子 factorization of this one. Okay? And you ignore this one. It's not important anymore. Yourself all the time. Probably I will delete this lecture the next year. So we create the eigenface. Eigenface look like this one. It's look like the film of the face. And then we remove based on eigenvalue. We remove. We only keep the first 7 biggest eigenvalue become your eigenspace. So after we so how can we decide? How many eigenfaces we want to have? How can you make a decision? The way is this one. So suppose you first of all you sort your eigenvalue. In this example, suppose I have a total 932 images. Okay, I sorted, and this equation here. So in the denominator term, I summation all the eigenvalue here. So in our case, in this case, I have a 932 eigenvalue. So I sum up of them together, become denominator. And then in your denominator term, first one, I put the first eigenvalue. Oh, I find it take 60%. I sum first one, second one, it take your occupy become 70% until about 95%. I summation the first eigenvalue 2, 3, 4 until it is a larger than in my threshold is a 95. So here I submit some of them, and the first 10 eigenvalue become 96%. Okay, I stop it. That's meaning that's enough. That's energy. 就那个能量守恒原则，能量守恒 that's enough because the variance eigenvalue represent the variance. So the variance is good enough. So I just keep the first 10 eigenvalue based on this equation. And that's my eigenspace. Okay. And your eigen. So you right now you have an eigenface. And then what I try to say is that this page 41, I want to explain to you the projection weight here. You have eigenspace. We want to do is that we want to have the projection weight here. What's projection weight? It's meaning each input image, new image, test image, or original training image, okay? Each image minus average value. And this is the result. Original image, you need to subtract the average value. This meaning bias. From bias become unbiased. And then you project to the eigenspace. Then our eigenspace only have 7 eigenfaces. So projection meaning inner product. So you have 7 eigenvalue here, omega is a projection weight. So each projection weight, each image has corresponding projection weight only 7 dimension. That's your eigen projection weight. We call projection weight here. Projection weight. That's it. You are done. Okay. So after you have a projection weight, next step, the two purpose. One, we can do the classification based on, I explain to you. I do the reconstruction first. And then later I will explain to you the similarity measure for the detection of declination. I'll explain to you soon. So next step, based on the projection weight, actually I can do the reconstruction. How can I do reconstruction? Okay. Easy. So each projection weight, you times with the original eigenface. This one meaning here. Each test image you project on the eigenspace, you have a projection weight. In the other word to say, based on the projection weight, you can reconstruct back to the original face. So this projection weight 1, you times with the eigenface 1. Projection weight 2 times eigenface 2. So you time all together, you can reconstruct to original face. That's a reconstruction. That's easy. And this is linear combination. This is the equation way. But actually, if you do the vector and matrix, very easy because you have 7 dimension vector directly times the eigenspace, this one. 你就有个向量乘上这个系数，你就可以搞出来一张五项，对吧？这是能力。So that's the mathematics this way. After you do the reconstruction, you got the reconstructed, but you need to plus original average face because each image you need to subtract with the average image and then do the projection. And do the reconstruction is meaning after you do reconstruct, you need to add or plus your average value become original image. That's reconstruction. Okay, we check this one. This original image, if you project to the eigenspace, it become only 7 dimensional vector. And then we do reconstruction. This is the reconstruction result. And you will find you will lose the details. Why? Actually, because at that time, that's about this paper, okay, they do not do the alignment well. Here, they do not do the alignment well. What's alignment? It's meaning actually we have a pre-process. So based on that, because each face, some are bigger, some are small. So for the detail, you need to base on the inner corner points of ice. Each one you normalize. So you have a template. So each image based on 2 points, you should project to this align with the inner corner ice. 就是说，它这个为什么模糊掉？事实上，原因在哪边？原因是说，你实际上在做这种 PC 的时候，你这样影像大小跟人脸大小一样，所以你要根据眼睛的内眼角两个点，然后你有个 template， 你要 match 到这个，就 project over to this template. So everyone, no matter is a bigger face, small face, you need to align to the template. So everyone has the same size of faces. So they in that time they don't do the pre-process of alignment, ALIGN and MEN2. So when you do the PCA for recognition, the first step you need to do the face detection, and then you also need to detect the inner corner of two eyes, because this inner corner of two eyes is a fixed point, affine point. They won't change by your facial expression. So based on both points, everybody have the same size of the face. That's building. And then, so that's why this become okay. One powerful for icon is that if you input in this one, we have a mask, occlusion. Actually, we can recover back to the original face. It's very powerful. So when you do the deepening, the same deepening, they'll tell you, okay, even though some image parts are missing information, I can recover the back. 在 deep learning 的时候一样，是一样的道理的，不是 deep learning。deep learning 这样做是以前在做那个电脑视觉的时候，根据 eigenspace， 你纵使有些地方是 missing 掉了，还是可以把你认出来。So why right now deep learning is very powerful? No, because PCA is powerful. Because we have eigenface. So that's meaning rectify to here. So suppose this one, right? Original face, you have some missing information. You project to the eigenspace, and then you do the reconstruction. Actually, we can recover your missing component. That's very powerful. So the same thing here. You project this face, you have missing data. You project to an eigenspace. Because eigenspace keep all the information of your features, so they can be shoved back to this one. So the same, we do the projection and recover, projection recover here. If we project a flower to the eigenface, actually you can reconstruct the face because all your eigen information are faces. So no matter you project any kind of information into here, they can reconstruct the faces. OK， 这是 PCA 的道理啊，因为你的空间就是全部都是你在你的空间里面都是人脸啊，是这样子。好，那个 that's for reconstruction. So the same as GAN, but GAN is more powerful. Why? I will explain to you soon. Why GAN is better than PCA. And the reasons are here in page 52. 52, I will explain to you soon. Why GAN is better than eigenspace. Check one. So for the similarity measure, that's the reconstruction, but back to the similarity measure. So if we have a projection weight here, the similarity measure, one way is just do the Euclidean distance. So you have original, you have 16%, you project to the eigenspace corresponding to 16 projection weight. Each person is one 7-dimension projection weight. So new image inside input, you project to eigenspace, you become 7 projection weight, and you just do the Euclidean distance for the similarity measure. It's one method. Or you can use the Gaussian model become likelihood. So each one is 7 dimension of projection weight, and you can do the probability here. So either way, so that's a similarity measure. It's easy. 相似度量测. So let's start. The final step is can we use neural network to represent all the mathematics 我们能不能用类神经网络来取代刚刚讲那些数学式子？所以 MIT 这篇 paper，MIT this paper，and Major I know the Major，he's essentially he's short。我们两个都不高，美国人都不高。Major he right now he's in Santa Barbara，我认识，因为同个时代的。But at that time he is in MIT do the face recognition，I'm in CMU do the facial expression recognition。所以我们就这样认识的，因为 MIT 那 Media Lab 跟我们还是有些大家会就不美国人是这方面比较好啦，就是那种所谓 top 的那种不是实验室，他们是以所的 institute 的，我们会交换就是你去那边演讲，来这边演讲这样子，所以我们都会得到最新的知识，就是你们 paper 还能就 in United States at that time I was in CMU, Robotics Institute. We are best one in the United States. And at that time, MIT Media Lab is very famous. Actually, MIT the most famous lab in India. They have a lab for AI lab at that time. AI lab 比那个还强，非常强。So we have sometimes we go there to give a talk. The student come here give a talk. So before you read the paper, we already know the new knowledge. So they're very open mind. In Taiwan, that's our weakness. In Taiwan, we are closed mind. We will keep all this our secret. I'm the best in the world. I won't tell you. It's Taiwan. It's not good. Okay. Actually, you are not the best. Anybody can beat us. Up here, so how can we do the neural network to represent? So this paper, the paper, the important one is not the eigenspace. The important one is here. So I tell my student, when you study a paper, a good paper, they have a good three things. One, they have good figures. They have good table. They have a good equation. Not complicated equation, no. Simple equation. So figures are very important for the paper. So when you find a paper, if they sometimes I check the paper for my student. I check it very quick. Every 10 minutes I can check it. And my students ask me, oh, Professor, then why you can check the paper so quick? I say, because I just check the figures. Best paper, the good figures. That's simple. And the other thing is, if you also I check the equation. If the equation are too complicated, don't use our paper, because we are application person. We are not theory person. We don't do the mathematics too complicated. Okay, here. So what's the neural network here is this original image. So this image size, 2D image size, original image. Okay, you do a subtraction. You got a bias, unbiased. So this is unbiased. And then we use neural network for training. We project on the, so this one is the coefficients of neural network, the same as deep learning. So this one is here. Each one is a neuron. This 2D, and before we input to the neural network, we need to be 1D vector, right? And each one is a neuron. So this is neuron. And connect to the projection. So this is suppose there's a neuron here. So input, you have 128 by 128 neurons in the node. You have this, you need to decide how many nodes in the second layer. So the second layer, in our case, is 7. So here's 7 nodes. This original 128 by 128 node is only 7 nodes. and the connection is the connection, the coefficients. Okay. So what's the coefficients? Coefficient is an eigenvalue. So there's one eigenvector connect to here, and the second eigenvector connect to second one. So see this one, Matthew Turkey created this one. From original vector, we have 7 projection weight in this connection. Okay, so connection weight equal to eigenvector component. Eigenvector. So the eigenvector. So based on this one, the connection. So this eigenvector, okay, eigenspace. So after you project, we can do reconstruct. So here, at that time, they don't do this one. They just copy this one to here. Because at that time, the computer is not powerful. So after they create the eigenvector, they just copy here to here. And then based on the same eigenvector, we can reconstruct to the image, reconstructed image. And you plus with the mean value, this one become reconstruction result. Okay. And if you put this is what projection weight. So any new image you subject with the mean value, you project to eigenspace, you become projection weight. So based on projection weight, based on the Euclidean distance, you can do the phase recognition. So this is the contribution for this paper. So for this paper, actually it's a deep learning kind of. So what's the difference between PCA and the GAN here? Sorry. GAN will be here. Let's explain this one. I'm done for this paper. This is PCA. And for the we call DC GAN, there's an easy one. There are many kinds of GAN, but this easy one is this one. So this one is this way. This encoder, I will explain this one and then I will close the class. Okay. This encoder, right? We train encoder, we train the decoder. Now we will find out because the encoder coefficients as a feature map are different from decoder. So that's meaning for eigenspace, your eigen, this one, eigen in encoder and the decoder, they are used the same eigenvectors. But in GAN, the encoder coefficients are different from decoder. 就系数就是我们在古时候做这个 PCA 是，它直接把 encoder 这个结果 copy 当 decoder 用，好不懂？它也不是那时候没这个概念，能够做出来就很厉害了。但是在我们现在这个时代，它的因为这是 encoder 这 decoder 直接 train， 那你 after you directly train, you'll find your encoder coefficients are different from decoder coefficients. That's powerful. That's more powerful. Okay, so this is I just give you a concept. This is an encoder decoder, but in GAN, they just cut it. 把它切掉了，切掉什么？ They will become this one because any projection weight we want to reconstruct to the original image. So this generator. It just give you a projection weight. We can generate the result, and we have a discriminator to identify it's a real or not real. It's a fake or real image. So both real is input original image become real, and fake is from generator. Okay, I won't explain detail about this one. The important one is the GAN, the encoder different encoder coefficient is different from decoder coefficients. Okay, I briefly explain to the about the gain. Gain is this one. You have adjustment weight or some we call latent code. Latent code is this one. This is latent code, like a descriptor. So a descriptor, suppose 100 dimension, we can reconstruct a face. And then you have ground truth face. You have ground truth face. For the generator, you hope both faces will be similar. That's generator. You generate a result. This is fake image. You hope fake image is similar to the real image. So both are as close as possible. However, we have one constraint here. Constraint is the same. In the other way to say that they know you have fake, you have real. They hope both are as different as possible. So if this is a real input to the discriminator, they'll identify to be 1. If it's fake, they'll identify to be 0. So both are conflict. So why GAN called generative adversarial network? This meaning conflict. 它是两个是矛盾的。So there are 2 loss functions. The first loss function is for generator. They hope both the fake and real are as similar as possible for the loss function. However, in the other constraint we call discrimination, we hope both they can identify this. If we input the real, it will be real. If we input is the fake, it will be fake. So it's both loss function are confliction， 这两个是矛盾的，这样是对抗，或者是对抗这样。那最后就会因为矛盾，它最后产生是这两个的越相似这样子。那你 train 完以后 ，this is only for training, but when you do the test, you don't need discriminator, you only need generator. For the test, you only need the generator. Okay, so this concept is exactly from this concept. 这两个 concept 是一模一样的。The only difference is for traditional PCA, encoder equal to decoder. For GAN, encoder different from decoder. It's better. Okay, so that's for this PCA lecture. Okay, and next week I will teach you LDA. LDA is for discriminator， 就是变那个做 LDA is for this discriminator. LDA 是做分类用的。And then I will teach you vector quantization for cluster, and I teach you Hinderman-Markov model for MAMBA. MAMBA is a deep learning MAMBA. 这样子 ，MAMBA MAMBA 这样子 ，MAMBA MAMBA. You can Google MAMBA. It's a very new technology for deep learning for tiny object detection. Okay, so that's for today's lecture. For the final exam is the same as similar to the midterm. So for the exam I will give you this concept.